Hello everyone. We're going to get started. All right, let's go to, you guys are section 1, Wednesday. Let's go here. All right, so we've been discussing singular value decomposition since last week. If you remember, I had some issues with the computer on Monday, but I was able to record that lecture on Tuesday, so that video is posted, so you can take a look at that if you fell behind. And that one was, we had covered so far the theory of singular value decomposition, then we discussed the recommender system itself. So today we're going to so I think I call that part 1, I believe. So then this today would be part 2, okay? And we're going to go over the code, and essentially once we finish the code, you'll have a working example that you can then use for your homework assignment. I will also assign the homework. I'll give you 2 weeks for this one. Essentially, there's like 2 hard things here. Yes, please. I don't think so because we had an exam, right? So there wasn't any. Yeah, no, there shouldn't be anything due. No. Yeah, I owe you a problem set, but I'm still working on that. So that you'll do by hand or something. Yeah, so and I want to talk about that in a sec. So the recommender system is what we're going to discuss today, and then there's 2 hard things about it, right, that you essentially will have to deal with. Number 1 is the data, right? So, that's your challenge, as I've said many times. 80% of the hard part of data science is actually dealing with the data. So you need to find a data set. I recommend trying to find something similar to the data set that I'm going to use today, but just for something else, like maybe, books I think are a very popular thing, recommending books, recommending, shoes. You could cheat a little in the sense that you could ask ChatGPT to generate data for you. That could be okay. Okay, so it's something to think about, right? But because it's synthetic data, you never know if actually the results are going to be what you want it to be. But that's always a possibility to think about. Does that make sense? So that's what we're going to do today. We're going to go to content here, and I'm recording, as you can see, table of contents for section 1. This should be pretty interesting. The code works fine. As I said, there's 2 hard things: dealing with the data, that was 1, and number 2 is getting good results. And that's where you now have to start putting on your data scientist hat, right? And you have to start figuring things out. How can I make this better? As I've mentioned, singular value decomposition does not like sparse matrices, does not like matrices with lots of zeros. So, see if you can address that somehow just by removing rows that have all zeros, things like that. So it's entirely up to you how you clean the data, but, that can help you out. So those are the 2 hard things. So getting good results, and I'll mention a few things today, and then getting a data set that's, and loading it. So this is essentially where we are, and you can see I have a link here, this link, which we will look at in a second about the code. If you look, I'm trying to finish this topic today, essentially, but singular value decomposition is not going to go away. It's like a very important concept in machine learning, even though it's a very classical method, because it helps us along the way to provide contrast with lots of things. So you guys have used regression already. You used linear regression, right? A little bit. I'm sure if you've taken a stats course, you've looked at linear regression there. As we look at neural networks, you'll be surprised perhaps when you see that neural networks are actually a regression. They're actually a linear regression, right? Or a nonlinear regression. So that's going to be very interesting, and you will also be surprised that there's a couple of ways of solving a linear regression. One of those ways would be, of course, with neural networks, but one is with singular value decomposition also. That is usually called the analytical solution. So, when we talk about that topic, it'll come back again. It's a short little script, and we will discuss, what's going on there. but it should be pretty interesting. All right, and so I'll use that to contrast. As you can see, once we're done with the singular valley decomposition, we'll begin our sequence of neural networks. We'll start with, the perceptron, linear regression, something called, I'll give you the history. This is going back to the 1940s, right? So back then. Then you can think about, then we're going to talk about Hopfield networks. That's another type or idea of neural networks later in the history. The gentleman, Hopfield, that invented this idea won a Nobel Prize in physics for this very algorithm. Like 2 years ago, along with Geoffrey Hinton, who invented stochastic gradient descent, which is the technique that we will use to train neural networks. Why is that relevant? Well, I've mentioned to you in singular valley decomposition, right? It's somehow there's an algorithm created by a human. We are guaranteed a decomposition of 3 matrices from one, but the values in there have to be calculated somehow, right? Those numbers. And there's an algorithm that people invented, but then Geoffrey Hinton advanced this idea that neural networks could actually solve that. And so he invented the learning algorithm that neural networks use. And what's different there is now he created a technique that allows a machine to learn, right? To learn the algorithm. Before, for singular valley decomposition, somebody wrote an algorithm. All the steps, here's the values. With neural networks, there is no such algorithm. Instead, there's just a framework that allows you to it's like the neural network in its mind, if you will, in its connections, creates the algorithm. Do you guys see that? It's different. So there's code in an algorithm for SVD. That solves linear regression. No code. Instead, that code that would provide those values is somehow embedded in all the connections of the neural network. So you create now a general framework of connections, etc., values in a neural framework, a lattice, if you will, and somehow that can learn an algorithm, right? But there has to be yet another algorithm, right? And that's the one that provides just the learning capability, and that's called stochastic gradient descent. We'll talk about that quite a bit. So the next third of the class, at least 4 to 5 weeks, will be neural networks, so we'll spend quite a bit of time. So you can see here, and then multi-layer perceptron, you guys are familiar with that, and then we essentially get to the end. I'll be introducing PyTorch at some point, like around here. All right. So yeah, so that's kind of where we're going, and today here we are, singular valley decomposition. So we're going to get started with our code. So I'm using this example here, recommender. And if you remember, in the previous class we talked about the data, so if you want to follow along, make sure that you download movies.csv and ratings.csv, these 2 files. These are the files that you need to get off for the homework, off the internet. And so we're going to learn to load them and learn to generate our matrix. So remember, we're using singular valley decomposition for this example, so we need to have some kind of an X or A matrix, and we're going to apply our singular valley decomposition to it to obtain 3 matrices as we discussed on Monday. So it'll be very similar. All right, so I should have that data already on my Google Drive. So what I need is, I need to open Colab. Okay, so I'm going to open up Colab here. Okay, and I'm going to mount the drive. Okay, and then we're just going to copy the path. So I'm going to go with ratings and movies. Okay. All right, so now just we can follow along with the example. Basics, SVD recommender system. So I'm just, I had already gone through this, so I'm just going to copy this part. Okay, so you can see the libraries, numpy, pandas, the cosine similarity, which is like the Euclidean distance. Remember, I'm basing this off of a data set called a movie lens data set. And we can bring in the files here. We're going to need the special path for that. Just like that. Okay, and you can, from there, use pandas to kind of look at individual values, such as the user IDs, movie IDs, and so on. So we can run this. And this is just to illustrate, so you can see the ratings file has, it's not a matrix as we needed. Instead, the data is more practical to collect data like this. Every row is a rating. So every row is mapping some user, let's say your user 7 to movie 33. And so that user rated that movie and said that the rating was a 4.0. Okay? So that's essentially what we have here. But we will need to create a matrix that is movie IDs by user IDs, and then where those two meet, that's where we populate the actual value. So I'll provide the code for that. So let's go ahead. Now we're just going to load the data, both files that we need. So one is going to be called data ratings, right, which we just saw. The other one is going to be called data movies. We can look at, for instance, data movies also. Oh yeah, and I need to change the path. Okay, and then this is going to be movies CSV. So movies CSV. Right, and there we are. So we have a whole bunch of movies, Toy Story, Jumanji, Grumpier Old Men, but you can see that the ID is, 1, 2, 3. These are the numbers that we will need. Okay. So here we are. Now the key question is we need to create that matrix that we're going to decompose via singular value decomposition. Okay, so this is the key part. Notice that in the example I gave you guys, I did 7 users to 5 movies. Do you guys remember that? We did that on the board. You can reference the video also. So users to movies, but notice here I'm flipping the matrix. Do you guys see that? Now it's going to be movies to users, okay, which is more correct so that we can use the first decomposition as essentially the compression that we're going to look at, okay? So NP zeros, yeah. So we have shape 9,724, so that's 9,700. I got that number by printing the shape. You can, of course, do the same. So if you're wondering how I got those numbers, you can just print the pandas data frame. So for instance, for movies, right, it's data movies, like that. You can see it tells me 9,742. 9,740. Yeah, 42 rows. Not 9,007. So I have 24. I wonder. It doesn't give me an error, so these are the rows, and those would not be skipped. Well, we'll take a look. Maybe I didn't include the last few movies in that, so we can certainly fix it. Okay, that's why sometimes not a good idea to hard code things, right? So get the numbers automatically, so you don't even have to worry about it. I may have flipped them. We can take a look also at the other one, which is data. So we have here, how many users? I think we can see there's got to be 610 users, I think. But let's, yeah, this is movie. So data reviews. It's not data reviews. Oh, ratings, sorry. Data ratings. Data ratings. And there we are. So we have, yeah, 610 users. Okay? So we just want to make sure that we have enough values there. Movie ID. Okay. So the IDs are the key thing. Well, there's a couple of ways. I guess we could map ID and just have a very sparse matrix. Keep that in mind, right? So we don't want a sparse matrix of zeros. Do you guys see what I'm saying? Like, we need to have some kind of a mapping between ID and row number. Because if I did based on IDs, which is possible, then what does that mean? I have to have 100, and if this is the movie ID, yeah, 193,000. But it's skipping values from 587 to 609, right? It's skipping a lot of movies, so we would have a lot of zeros in there. Do you guys see that? So this is me trying to solve that problem a little bit. But it makes the code a little bit more complex, okay? Anyway, so we create here a matrix, and that's what I was saying for you guys, that when you do your homework assignment, this is actually the hard part. Once you have that X matrix, you just use one line of code, it's decomposed, and then you proceed to try to recommend, so via some kind of a distance metric. Okay? So here we can run this one. You can see it is currently a matrix full of zeros. It's NP zeros. Okay? The values are going to be integers from 1 to 5. 0 may be present, and we may not want zeros in there, so that's another value, even when we have a rating. Another issue that you guys are free to control. All right, so now that we have the matrix, okay, we printed it. We have the shape of it. So we can proceed to, this is probably like, the part, we have to create these dictionaries, okay? So let's go ahead first and just grab from data ratings. So data ratings being this one, we're going to grab the user IDs as a list, right? The movie IDs as a list, and the rating as a list. By the way, this code could be written in various ways. You might actually be able to write a more efficient code, but hopefully this is simple enough. But essentially, we're just grabbing these columns as lists. So you can see that over here. So I have a ratings array, a movies array, and a user IDs array, right? All grabbed from that data ratings, from the column, the corresponding column, rating, movie ID, and then we just grab the values. So essentially in a for loop, right, I go from I to the end of this, and I can just grab each, with I can grab by index, let's say I grab rating 3, then I grab movie 3, and user ID 3, the entry 3 in that list. Okay, so it's going to map. So I'm just going to create that for convenience. I don't need this anymore, so I'm going to get rid of it. Okay, so I have that. Then let's notice we're going to create these dictionaries. which add a little bit of complexity for sure. So we're going to have a movies uniques dictionary, ref real, okay, and a movies unique dictionary real ref. And essentially they're the same, but a reverse dictionary, they're called. This is just to speed things up a little, okay? They're going to be this. So if I have ID 3 and that's movie 17, right? So 317 or 17.3. And that's just to make the search a little bit faster. Okay. Now we're going to go ahead and create here. Control copy. Okay, so movies uniques, NP unique is a function. It's going to look at the array movie IDs and it's just going to return all the unique IDs for a movie. We can also print these. And you can see there they are. These are the movie IDs. We can print, this is a numpy, so let's try length of movies unique. 9724. So this is where I got the number. See, it does match, 9724. Do you guys see that? So there are unique, these are the unique IDs, okay, that we have in our matrix. But the real IDs go way higher to 193. Could be that what happens is maybe you have, these are just movies, but between 193,587 and 193,609, you had TV shows or you had music videos or something like that. You see that? And so as the data was collected, but everything had a category, like this is a TV show, primetime TV, or network television, sports versus a movie. So you can filter them out. And that might be a common thing that happens, right? You just have this database, and now you extract the data from the database, but to use it in machine learning, you're going to have to tweak it a little bit more. All right, so now comes this part. So we're going to do this for loop to fill in the dictionaries, okay? And that's this part here. So if you notice, we're going to iterate. We're going to use the enumerate function over movies uniques. Okay. So we're going to map essentially the actual ID to the index position that it's in, right? So for instance, I'm going to iterate through movies uniques, which has a size of from 1 to 9,724. Do you guys see that? So essentially then when I have IDX for 9,724, what is the actual value that goes in there? This one, correct? The actual ID. And again, this is just to avoid having all these zeros, because zeros would be bad for the SVD. Is this clear, guys? Any questions on this part? All right, perfect. So yeah, and then the other thing where we do rest, so we do, if you notice, given the index, we assign the actual value. So given 9,724, I would assign 193,609. And usually in machine learning, when you have big things like this, because dictionaries are actually hash tables that run really fast, it's better just to have them the reverse of it so that the reverse is also fast when you're doing the lookup, as we will need it later. So then I have here, if I have the rest, which will be 193,609, it's going to return 9,724. It's just that map, a simple mapping, essentially. All right, so I run that, and there you are. I have my dictionaries now, so I can then build a smaller matrix. Also, a matrix that is 193,000 actually would be pretty big, right? So that's another problem that we probably don't want to have. So it's worth adding this slightly more complex logic. Okay, so we did that. We look at the users. So I'm going to copy this part over here. Okay, so I'm going to create two dictionaries again. Users, uniques, dictionary, ref real, and the reverse one, real ref. I want to get the user uniques, how many I have, and these are going to come from the user IDs array, okay, which was these three that I got over here. Okay, and I grab the uniques, and then I can print them and also check the length. That should be 610. So if I run this one, you can see the values. See, this one does not seem to skip anything, so perhaps this was not necessary, but to be consistent. Okay, so let's grab users uniques. Let's just check the length to make sure. We want to check the length always. So 610. So here we have our unique number of IDs, user IDs, and also movies. Now we're going to perform similar approach with the two for loops. We do the mapping. We use our enumerate, which we've used quite a bit this semester, over the user uniques, right? IDX res. So we grab the ID X 610, and it's probably 610, right? So that's, it might be offset by 1. So we can check that out if we would like, just to see, because it's not even that big. We can take a look at it. That's a dictionary. Yeah, so it's off by 1, right? You can see it's 552 to 553, so essentially the user IDs, there was probably no 0 ID or something like that. Okay, so we don't, that's too big, so we don't really want to, whoops. Yeah, whoops. Yeah, so see, it's 0 to 1 mapping. And there we are. So that is done and addressed. Okay. So now we can proceed now, if you notice, to fill in our A or X matrix, which is now the matrix that we can then decompose, as we did in the example. So we're going to fill that in. This is going to be our matrix that we created up here somewhere. Yeah. So our ratings mat for matrix, right? So of size 9,724, comma 610. Okay. So this one is here. So we're going to take a look at the code. So we're going to grab this first part here. All right, so I'm going to essentially just grab one of the arrays. I don't have to grab, so let's see. Ratings array, right? So let's go back here. Ratings array. Remember, I have these 3 arrays that I grabbed from that file, ratings. So ratings array, movies array, user ID array. So remember that all 3 are the same size. So to determine the length for all 3, I just need the length for one, and then I can iterate through them. And I'm going to index the value accordingly. Okay, so that's this part here. So length of ratings array, so I'm just grabbing the one that has the rating value. Rating. Okay. And for I in range, and I just grab the I as an index. And then I can index from user IDs array, I grab the U that's in there, right? Do you guys see that? So that would be like 193,000, sorry, that would be 610. And then from the movie IDs array, I grab the index, which would be what? Let's say the last one, 193,000 something or other, right? So that very big ID. And I just store them in U and M, okay? So that should be intuitive. Then, of course, I don't want to use those values because of the sparsity issue of singular value decomposition. So I need to grab U and M, and I need to plug them in the dictionaries that I just created where I have my mapping, so that if my ID or for the movie is 193,000, let's say something, it returns 9,724. You see that? So that's essentially what's happening. So I grab U, I plug it in the user's uniques dictionary real ref, and this is going to give me now the new mapping, right? Which for the users is only offset by 1. But for the movie's uniques dictionary real ref, I grab M, and so this is the mapping from 193,000 to 9,724. So this is the little trick. And so now I have the values that I'm actually going to use in this more not sparse matrix. And even though this is really great for at least 2 reasons, not having a huge size for computing purposes, but also for the SVD to work better, I will print it in a second, and you will notice that it's still pretty sparse, right? And so that's an issue that I'm raising with you guys for you to try to address somehow. Okay? So let's take a look over here. So now my ratings matrix, right? I can just say, okay, well, reference movie, whatever it is. Let's say that's the movie 9,724. And this was user, for whatever reason, 215. And so we know that the rating, because these 3 matrices, user IDs array, movie IDs array, and ratings array, all match by index, right? They're in order. So I can just use the same index to grab the corresponding rating. And there you are. And now I have succeeded in populating my matrix. Do you guys see this? This is what you guys also need to do for your homework assignment. You know, you will find some data, but in the end, you need to create this matrix over here. Any questions? This might be one of the challenging parts. Okay? All right, so I'm not hearing any questions, so I'm assuming makes sense. All right, so I'm going to go ahead and just check. See, this for loop then would complete. So let's give it a minute. Actually, it ran pretty quickly, right? And it is now done. So great. So ratings mat is actually the X or A that will go into our singular value decomposition function to return our U, our S, and your V. Now you will be able to get the 3 matrices that we need, and that's really great. Let's print out, though, some of the values just in case. So this one's easy, the shape. We had already printed this, so this hasn't changed at all. That's the same 9, 7, 24, 6, 10. But this one is more important to look at. So you can see here, I'm only slicing, right? Because the matrix obviously is 9,724 rows. So I'm only going to print a few rows and a few columns. We could probably have more columns. It just depends on whether it's going to fit. And let's do like 40. Oh, okay, that's too big. All right, so that's probably. So let's stay with 20 and 20. That gives us enough data. Yeah. So as you can see, so this is the matrix. Remember, it's movies, right? Movies on this. The rows are movies. The columns, 610, are users. So that means that let's say that we grab this movie. Let's say that for whatever reason this is Star Wars, right? So then one user here gave it a 4, another user here gave it a 5, another user gave it a 3, and so on, right? So actually this could be used for creating, like in Rotten Tomatoes. You guys have, Rotten Tomatoes, right? Movies have like a score. This is how you calculate it. You would grab Star Wars, you average all these, and that's how many points you get for that movie. So that's how you would do it. But anyway, the issue is, if you notice, there's still quite a few zeros here. Okay? So to improve your results, which is the second challenge, in your homework assignment. You kind of want to deal with this somehow, so I'm leaving that as an open question for you to research a little bit. And I'm not saying exaggerate in your attempts, but just do your best. Do you guys see that? All right, so that's one issue, just to get a feel for what data science is. Data science is about, this is the reality of your data. You have techniques, but at the end of the day, what do you want to do? If it's the Netflix challenge and they're going to give you $1 million to whomever writes the best algorithm, right? So what's your objective? You want to win that competition and get that $1 million. $1 million 15 years ago is a lot of money. All right, so you can see this here, right? So that's essentially the idea. Okay, now we have our data. Okay, so let me, I'll just do 10 here so it doesn't take up too much space. It's taking a while. First one. Okay. All right, well, I don't know why it's taking so long. All right, so once that's done, guess what? We have this amazing function, so everything that we learn, all the math and everything, right? And at the end of the day, this little function here does our singular value decomposition for us. So we can go ahead and copy these. Okay. And now we're going to just add a few more cells. All right, so as we've discussed in the theory, you understand now what these U, S, and V mean. You understand about calculating the number of components, the singular values that define how much energy you have in there. But we're going to give ratings mat. Now the theorem here becomes very powerful. It says any matrix M by N is guaranteed to have a singular value decomposition. That's pretty powerful. There are other techniques like PCA, etc. They have conditions, right? But this one does not. So then we're going to take in our ratings mat, run it through the singular value decomposition, and get our 3 matrices, and we can go ahead and do that. So it's taking a little bit, as you can see, because it is big, and there is an underlying algorithm, but doing this processing. We're going to give it a minute. We can also print out the values just like to see. So it finished, which is good. It's not going to give us all the data, but we can just look at it quickly. Well, actually, it prints out a lot. All right, so you can see there the data. So a lot. Okay, so maybe not so useful, as you can see. But here we know that this is pretty important. It gave us the matrix U, the matrix S, and the matrix V. Okay, so it has created, and these are, by the way, okay, so let me here, hold on, I have a little correction here. So pay attention to this part. Yeah. So remember, as I said in the discussion, the singular value decomposition, there's like the full matrix, and what was the name of the one that we kind of concluded or finished our discussion at? It was called the truncated SVD, right? So the truncated SVD. So if you notice, when we ran the code like this, it gave us the full rank, the full range, 9,724 by 9,724. Do you see that? So it gives you, but we want, let's try this one. We just notice that all I'm doing is I am same function, same matrix. I've done something here, and I'm using this parameter full matrices equal false. Okay, by default it's going to be true. So let's just add that little parameter in here. So comma, full matrices false. Okay, so I'm just doing that. Okay, and if I print, give it a minute. Note, do you guys notice that the number has changed here to 610? Did you guys see that from 97? That's important because really the way that we've discussed this in terms of like iris, let's say, this would be 150, right, comma 4. Do you guys see that? So that's the number of axes that we have, and then from there we would select the top 2 or 3 or so. Okay, so let's go with the truncated SVD instead. So this one gives us our familiar format. Does this make sense, guys? But from here we could select something more, smaller. So we have 9724 to 610, but we can calculate the values, the singular. Remember that this matrix here of size 610 has what? A singular value on the diagonal, right? Indicating how important the 610 are here. Remember that these 610 are no longer these 610. Do you see that, guys? So it still creates 610, but you can select, the first one is more important, then the second one, then the third one. That's how the algorithm works. So we can select actually a K that indicates which one, how many of these we want to use. All right, so that's essentially what I have created here. So I have my U, my S, and my V. Okay, and this is the same here. Of course, these would be the principal components that represent the users, but we are more interested in the movies in this example. This will be a thing that you have to think about in your, in your assignment. What are you trying to recommend? Are you trying to recommend movies? Okay, then focus on the movies part, over the users. Maybe you're trying to recommend a user, and the only scenario I can think of that would be something like Facebook or something. You know what I mean? Like, does Facebook have a feature where it recommends people that might have the same interest as you? Does it do that? Do you guys know? But you can imagine it might do something like that, right? So it gives you, hey, these 3 people here, I recommend to be friends because they probably like the same hobbies or something, okay? Or they're in the same major. So that's essentially the idea, but in this case, we're just focusing on the movies, for instance. You'll have to make that decision in your homework assignment. Okay, so we have that there. Okay. So we can, let me see if I have this function here already. So okay, yeah, so let's go to the repo, SVD. We did this example in compression, I believe. I think here. And we calculated the energy, essentially. So calc energy. Actually, copy the whole thing. All right. So we can go over here then. So NP, we have S. We square it, so let's see that part first. Okay, they're squared in a vector, right? If you remember, we did that. And then I'm going to just select a K. Let's say my K is going to be equal 2, and I'm going to plug that in here as K instead of 2. Okay, so if I run this, 0.24. What does that mean? If I gave this as a question to you on the exam, what did I just do? What does that 2 mean? 2 principal components, right? So that means that every movie would be represented by just 2 instead of 610. Do you see that? So that's essentially, but what's the problem with that? 0.24, what does that mean? That's the amount of information that has been stored. So that means that you're probably losing some information. Do you guys agree? Okay, so maybe that's not enough. So let's try 50. Okay, 58. Better, but still you might be leaving something there. So this has 610, right? So 200 perhaps. 86. Do you see that? So you'll have, and this, you'll have to play with this value as you will be doing this for, you're all going to have different data sets. So you need to figure that out. But let's leave it at, if I do 300, because that's still big, but yeah, 93, you see that's much better. So maybe K should be 300, okay? All right, so that part we've done. Let's go back to our recommender. Okay. And we printed this. We already calculated our U, our S, and our V. We are going to use a function such as this one. You can replace it if you'd like. This should be familiar to you as we did K and N already. And if you remember in K and N we used a Euclidean distance. So here we're using the cosine similarity, for instance, if you want. So you can use the cosine similarity, which, you can use the built-in or this approach over here. So function to calculate the cosine similarity. This is similar to the Euclidean distance. It sorts by most similar and returns the top n. So this is actually very similar to K and N, if you remember. So how does this work? We create a function. We give it the data, right? The data is going to be the vector representation. So that for every movie, we have a vector of, say, size 300, which is the compressed version that we just figured out instead of using the 610 one. Remember, those are different components now. So we give it the whole data, okay? The whole data. We're going to give it the movie that we want, okay? The idea of the movie that we want. And we're going to say how many components, how many principal components we should use, which is this value that we just defined here, 300. And the top n, so it returns like the top. Because we want, it's a recommender, right? So we want to recommend the top 10 movies that would match in this case. Does this make sense, guys? All right, so here you can see. So for instance, I would grab, first of all, I just need the movie, but I need the vector that represents that movie, right? The vector that represents that movie is the vector in U, okay? That's the vector that represents that movie. So I just have one. I'm going to convert it to an NP array, and from the whole matrix, the 9,000 by, by the U one, which is this one, right, which is this one here, U. I'm going to give the whole thing, and I just tell it which ID I want, which row, okay, that's the movie, and then I give it, this will grab all the columns in there, all right, so I need to do the K either here, this doesn't do it inside, it does it outside. Okay, so it's going to send, you can assume here that you already actually just sent 50 Ks. But you could also do it here if you'd like. So how would you do it? Just like that. Does that make sense? So it's up to you. All right, once I have the movie, then this is a very handy operation for the similarity. What is this NP dot? A matrix multiplication. That same thing that we've been doing, remember? That returns one value. So this vector is 50, this vector is 50. We perform that operation. So we do it actually between the movie row and every other movie in our U matrix. Do you guys see that? So I'm actually in one operation. Let's say that I'm the movie. I'm performing that matrix multiplication between every row. All right, so this is U, that is 9,000 by 300, and this is 1 by 300. So that way I perform this dot product, that operation, and that essentially gives me a value between this movie and all the other movies. Do you guys see that? And then essentially that's a distance metric, similar to the Euclidean distance. You can also replace this with the approach of the Euclidean distance if you'd like. And then once that's done, we record those in a list called similarity, and NP-arg sort, if you remember, sorts, right? So it's going to sort, and it's going to give you the indices of the movies that you are, in fact, recommending. Does this make sense, guys? So that's essentially the idea. And then here I have also other ways of trying this, but that should be good enough. So once you have that they're sorted, you return sorted indices until top n. So let's say like the top 10. So essentially those should be the top 10 recommended movies given that movie. Any questions, guys, on this operation? Should be similar to Euclidean, but just keep in mind this idea of multiplying a vector by another vector is a type of a distance or similarity metric. Okay, so the function has been included. Okay, so that part is done. Now over here then, we're almost done. If you look, we're almost done. That's like the hard part. So now let's just add some additional ideas. Okay, we're going to define some parameters. We said k is 300, right? We defined that here. We say k is 300 because we like the value 0.93. Obviously, you can add more. You can play with this metric as you like. This is just an example. I mean, it would be okay to have 99, but I just don't know how many principal components you would need. And then pick a movie. Do you guys see that? Pick a movie, 79132. Kind of just pick a movie randomly if you'd like from what you have. So once you pick a movie, you will need to, because obviously you need to use the real ID, right? So it's something like this. You need to go to, where is it? Yeah, so here. So let's say that you want the movie Andrew Dice Clay Dice Rules from 1991. Then you would need to grab 193.609 as the ID. Okay? And then you plug that ID here, right, in this where I have 79132. And then that needs to go in your reference dictionary, if you remember, right, so that it can actually give you the mapping to the ID that we're using, which was not going to, it's going to be less than, 8,000. Okay, so I should have then, I can print this one. And you can see 79,132, whatever that movie is, maps to 7,355 in our matrix. And again, we do this slightly more confusing so we can avoid all the zeros. Matrix that singular value decomposition does not like. Okay? Then now, notice here, we grab our U matrix. So notice we created ratings mat, right? That ran through singular value decomposition. It was decomposed into our U, our S, and our V. And now we use our U. There it is. That's our U. We grab all the rows because we need to send all the IDs. But notice here the K, I actually do this outside the 300. So I'm only sending a matrix that is what? What is the size of this U matrix? You would know it's 9,724, 300, not 610, right? Because you've selected those top components. So that's what we're going to send. Here it's just, you just grab it, run it through numpy to make sure it's a numpy array, and we're going to change the name to slice matrix. Okay. So now that we have that, then essentially we invoke our function that we just defined. As I said, use cosine similarity, use Euclidean distance, play with other distance functions, okay? But we're going to pass slice matrix, which is based on the U matrix, of course, right? One of the decomposed elements. We pass the movie that we want. In this case, 79132 original, which maps to 7355. This K actually is not being used because I already used it here, but if you can decide, if you want to change it in there. And then I want the top 10 movies that map to that one. That's it. So if I run this one then, top indices, and these are the movies that are recommended, and that's it. This is how it recommends the movies. And now, obviously, we don't know what that means, right? They're also not the original IDs, they're the mapped IDs. So we just have to kind of reverse the process and look at what these movies are. So that's the last part of it, and that's the code. So I just printed these. So let's do first the movie. All right, so we know that we need to search this movie. So search movie ID. This gives me okay, so now, trying to think, data movies. What was data movies? What was data movies? It's the whole pandas data frame. Okay. Data movies is the pandas data frame. And we grab, yeah. Okay. So it's here. So data movies. Oh yeah, so this is just because I had the original. I was confused about that. So I did have the original ID, didn't I? So that I had 79132, which is the original ID. So that's why this is okay. Do you guys see that? I do have it in search movie ID before I did the mapping. And so then I just look in data movies. I look at movie ID, which should be that one. Well, data movies, yeah. Movie ID here, right? So 79,000, whatever, and then it's going to give me the title or something. Yeah, that's fine. Okay, so yeah, so then it's essentially like an if statement, right? This is find where that ID matches, and then give me for that row that where it matches the title and the values. So if I print, the movie is actually called Inception. Okay, so that's the movie. Okay, so now let's add a few more. Did you guys do you guys have any questions on this part? I could have done it in another way, but this works fine because I do originally have the ID. Any questions? No? All right, so the next part then is now we need to print out these ones, right? We need to print out the recommendations. So let's do that part. Okay, so print, just a little statement here, print now recommended movies. We have our recommended movies in top indices, correct? So for ref in top indices, you can print the ref, but we have the ID. Now, obviously, remember, we have the ID in the dictionary, but not the actual ID. So we have to use our reverse dictionary. So if you remember movies, uniques dictionary, real to ref, we give it the ref, and it's going to give us the actual ID of the movie. Right? Any questions on this part? And then once I have that, I can print that, and I can also then do the same thing I did over here. Right? I'm going to go to the data movies, pandas data frame, find the movie that matches that ID, give me the title, and print, essentially. And there you go. What do you guys think? Any comments? Keep in mind, people recommend multiple movies, right? They have different tastes, so it seems like these movies would is what whoever liked Inception, would like these movies apparently. So that's essentially what the recommender system is doing. Yeah. That's it. You guys are not impressed by anything. Anyway, so this is we've completed the recommender system. As you can see, we've used singular value decomposition, this concept, right? That you have. I don't know if you realize, but this is a different kind of data set, right? In the past, we have done. It's similar but different. In the past, we have done things where we have iris, right? We have a vector of 4, it's got a class, a regression, something like that. We model that. We've done k-means. Now we have something called collaborative filtering, the kind of problem that's very common in today's world of recommender systems, right? So users such as yourselves go in, recommend individual items, you just collect that information, build a matrix, and from there you can proceed to do things. It would not be great to represent the data like this. It's better to represent the data like this. So I don't know if we printed you. Let me do that actually. So I'm going to copy this one. Okay. I'm going to go down here actually. And I'm going to change this to you. And you can see, notice that the values have completely changed. Do you guys see that? So when you guys did feature ranking in Weka, right? Feature ranking in Weka, essentially you would have had, you know, still the same data, just maybe you would have taken out the last 4 columns. Do you guys see that? But it would still be a whole bunch of zeros and twos, and because that's feature ranking. You were just selecting features. But in singular value decomposition, these types of elements, you transform the data into other things. So you can see the values are completely different here. Maybe to make it more visible, let's just do 4. Yeah, much better. So do you see that actually this are totally different values from here where we had these values. So they have been transformed by the system. Now, in the example I gave you, I said something like, this is probably sci-fi, this is probably romance, comedy, foreign language film, something like that. But I can't really say for sure, right, what the algorithm decided to do. That's just kind of an example. It could be much more complex. It could be like sci-fi from the 70s, right? Star Wars, all those space operas have a very specific following, and some sci-fi from the now, it's not going to be in the same interest even. Okay, so that's essentially the idea. So this is what you guys, so again, to repeat, this is what you guys have to do for your homework assignment. In a second, I will create the link, and then you guys can start working on the assignment. Okay? I do have another code. So you can see that's where this Jupyter notebook ends. So that's what I need to see in your homework assignment. I'll be looking for this screenshot. I'll be wanting to know like the energy, right? So I'll want to know like, where do we have it? Oh yeah, that's in here. So the calculation, how did you arrive at K, right? So you have to tell me that, you know, you had a metric such as that. Okay, and then you will print out the movies, given overall, or not the movies, you'll be doing another type of data. Maybe you're recommending shoes or recommending books or something. Okay, so that's the things that I'll be looking for. I do have another piece of code. Let's just go back, and it's this one. So if you go to the under repo SVD where you have recommender, compression, and other, I have this script here that I provided, and this just this works also as is. It's very similar to the code you have that I gave you. It just has a few tweaks, things that I been playing with, kind of give you some hints maybe as to how to improve, but it's very similar essentially. Okay, getting rid of zeros like these before SVD would possibly help out. Okay, so that's something to consider. And that one was for the movie Meet the Parents. So I guess that's a comedy, if you guys remember, from 2000. And it recommended a whole bunch of comedies, in my opinion. Bruce Almighty is definitely a comedy, American Pie. So all of these, I think, are comedies. Yeah, that's it. All right, so I'm going to create now the homework link. Yeah, so I don't need to record anymore. I'll stop the video here.